inverse circular functions and their graphs. When we try and find the inverse of a function, we know that it must be 1 to 1. So to find the inverse of a sine function, we can restrict the domain of the sine function to be between negative pi on 2 and pi on 2. And what that does is it makes it a 1 to 1 function. So it passes the vertical line test and it passes the horizontal line test, where it only goes through the function once when we go through vertically and horizontally. If we use this restriction, we can see here that our range is from negative 1 to 1. So our original function we restrict to be from negative pi on 2 to pi on 2, and that allows the range of that function to be from negative 1 to 1. When we look for our inverse function, we know that when we have an inverse function, our domains and our ranges swap. So, up here we can see that our domain was negative pi on 2 to pi on 2. That becomes our range for the inverse function. And we can see here that our range for the original function becomes the domain for the inverse function. We've restricted the domain of sine to be 1 to 1 function. Sine inverse is also a 1 to 1 function. In VCE, generally we restrict it between negative pi on 2. We could restrict it between pi on 2 and 3 pi on 2, 3 pi on 2 and 5 pi on 2, etc. However, the standard definition for the restriction of sine is between negative pi on 2 and pi on 2. Once we have restricted our domain and our range, we can see that our inverse function is a reflection in the line y equals x. So our original function, which is here in blue, if we reflect that in the line y equals x, we can see, let's make it a different color, yellow. We can see here that's our a reflection in the line y equals x. So we can see that's what our sine inverse function looks like, and its range is from negative pi on 2 to pi on 2, and its domain is from negative 1 to positive 1. Just like sine x, it's a continuous function and it's not 1 to 1. Cos x we need to restrict to be a 1 to 1 function as well. So what we have decided, or general convention, is to restrict the domain from 0 to pi. We couldn't go from negative pi on 2 to pi on 2 like we do with sine, as it wouldn't be a 1 to 1 function then. So we restrict it from here, negative 1, that's from 0 to pi, sorry, and when we restrict it from 0 to pi, our range, once again, is negative 1 to 1. To find the inverse function, we know, or to graph the inverse function, we know that our domains and ranges switch. So our domain here becomes our, our domain here becomes our range of our inverse function, and our range here becomes our domain of our inverse function. And cos inverse x is just a reflection in the line y equals x. So here's our line y equals x. This is our original graph, the yellow one, and our reflection in the line y equals x is our inverse function. You can see here the domain is from negative 1 to 1, and the range is from 0 to pi, which we have over here. Something I forgot to mention in the last slide. If you have cos inverse, that's also known as rcos, acos, or arccos, which sometimes they may do in exams. So sine inverse can also be known as r sine, a sine, or arc sine. With tan, one cycle of a tan graph is a 1 to 1 function. So from negative pi on 2 to pi on 2, our graph of tan is 1 to 1. It passes both the vertical line test and the horizontal line test. So we restrict our domain, in this case, to be exactly the same as the sine function. Our range is all real numbers, because it goes up forever and it goes down forever. For our inverse function of tan, it's also known as artan, atan, or arctan. When we flip around our range and our range becomes our domain for our inverse function, and our domain becomes our range for our inverse function. Now, I've just realized there that I have got square brackets. They should actually be round brackets. The reason being, this graph never actually gets down to negative pi on 2 or up to pi on 2. And likewise with the function tan, it should be from pi on 2 to pi on 2, negative pi on 2 to pi on 2, but with round brackets, because the graph isn't actually defined at those points. Okay, so I'm going to hopefully try and draw something similar to what a tan graph would look like. So a tan graph, they would be our asymptotes on our original tan graph, and our original tan graph would look like something like that. You can see here, that's a reflection in the line y equals x, sort of. That's a bit hard to do it on one of these screens. Our asymptotes, this asymptote is x equals pi on 2, and then this asymptote is x equals negative pi on 2. You can see that they switch, and it becomes y equals pi on 2 and y equals negative pi on 2. So that's the graph of inverse tan. Looks something sort of similar to a cube root of x graph. If we want to evaluate sine inverse of root 2 on 2, the first thing I would do is draw a special triangle, 1, 1, root 2, pi on 4, and pi on 4. We know that root 2 on 2 is equal to 1 on root 2. So in this case, sine inverse, sine is opposite over hypotenuse, so that means my angle must be pi on 4. So in this case, sine inverse of root 2 on 2 is equal to pi on 4. With tan inverse of negative 1 on root 3, once again, I'm going to draw my special triangle, 1, 2, root 3. My angles are pi on 6 and pi on 3. I'm going to tan inverse. If I have 1 on root 3, as we do up here, my angle must be pi on 6 because tan is opposite over adjacent. So in this case, my angle will be pi on 6. My primary angle is pi on 6. However, if we were to go to pi on 6, that's in the first quadrant. Tan of pi on 6 is not negative 1 on root 3, whereas tan of what angle is negative 1 on root 3? Well, in the last quadrant we know that tan is negative, so it's negative pi on 6. So in this case, our solution for tan inverse of negative 1 on root 3 is equal to negative pi on 6. And we know that tan inverse is, our values for tan inverse, they range between negative pi on 2 and pi on 2. This value fits into the domain, so into the range, sorry. That value there fits in between negative pi on 2 and pi on 2, and we know that it's negative. To evaluate, first we're going to evaluate the inside the bracket. So sine inverse of root 3 on 2. Draw our special triangle, 1, 2, root 3. Obviously it's not to scale. Not too neat. Okay, sine inverse. We know root 3 on 2. If I have root 3 on 2 and it's sine, Sine is opposite over hypotenuse, so my angle must be pi on 3. So sine inverse of root 3 on 2 is pi on 3. From here, we need to evaluate cos of pi on 3, and we know from our special triangle, 1, 2, root 3, pi on 3, cos of pi on 3 is adjacent over hypotenuse, so cos of pi on 3 is going to be 1/2. Okay, cos of 2 pi on 3, cos of 2 pi on 3, we know cos of 2 pi on 3, there's pi on 3, there's 2 pi on 3, it's going to put us into the second quadrant, and we're pi on 3 away from the axis. We know that in the second quadrant cos is negative, so cos of 2 pi on 3 is exactly the same as negative cos of pi on 3. Negative because it's in the second quadrant, and pi on 3 because it's pi on 3 away from the x-axis. So with our special triangle, 1, 2, root 3, pi on 3, and pi on 6, I want to find cos of pi on 3. So there's pi on 3, cos is adjacent over hypotenuse, so this gives us negative 1/2. Next, I want to evaluate tan inverse of negative 1/2. We can't use a special triangle to evaluate that. However, we do know that tan inverse of negative 1/2 is going to be exactly the same as tan inverse of 1/2, but negative. Because if we go back an angle that's negative 1/2 of a radian, it's going to put us into the last quadrant. So if I went back an angle of negative 1/2 a radian, it's going to put us back into this quadrant. That's exactly the same by symmetry as being in this quadrant with the same angle. However, we know that in the last quadrant it's negative, so we have to put a negative out the front. So you could have given your solution as tan inverse of negative 1/2 or negative tan inverse of 1/2. To find the implied domain and the range of a sine inverse 2x plus 1, our sine inverse graph has a domain of negative 1 to 1. So inside our bracket, 2x plus 1 must be between negative 1 and 1. If I get rid of the 1 and bring it outside, I end up with negative 2 is less than or equal to 2x, which is less than or equal to 0. And then if I divide my 2 out, I get negative 1 is less than or equal to x, which is less than or equal to 0. Therefore, our domain is x is between negative 1 and 0. Now to find our range. Well, our range won't have changed from a basic sine inverse graph, which is from negative pi on 2 is less than or equal to y, which is less than or equal to pi on 2. The reason being that there's no dilation, you can see here, so no dilation from the x-axis. We can also test it. If we put negative 1 into sine inverse 2 times negative 1 plus 1, we get sine inverse of negative 1. Sine inverse of negative 1, let's just draw a small sine graph here. There's negative 1. Sine inverse of negative 1 gives us negative pi on 2. If I substitute sine inverse 2 times 0 plus 1, I get sine inverse of 0, sine inverse of 1, which if we go over to here, there's 1, sine inverse of 1 will give us pi on 2. Therefore, our range for sine inverse of 2x plus 1 is y is an element of negative pi on 2 to pi on 2. When looking at this tan function, the values that we can substitute into tan are between negative pi on 2 and pi on 2. So it's say negative, let's change back to black, negative pi on 2 is less than 2 cos inverse of x, which is less than pi on 2, because our domain is restricted from negative pi on 2 to pi on 2 for tan. However, the graph of 2 cos inverse of x, that has a range. If you think about a cos inverse graph, it looks like that, but this one's been dilated by a factor 2. So instead of going up to what would usually be 1, it goes up to 2. So our range for this function inside is from 0 up until 2 pi. We know that we can only have values, therefore, between 0 is less than or equal to, because we can include 0. We could evaluate 0 up here, and we can evaluate 0 here. So 0 is less than or equal to 2 cos inverse of x, which is less than pi on 2. Okay, if we want to solve this, we can divide our 2 outside. So I get 0 is less than or equal to cos inverse of x, which is less than pi on 4. And then when I invert, if I bring the cos outside, I get cos of 0. Now, bringing cos inverse out has the effect of changing the sign around. So it'll become greater than or equal to x, which is greater than cos of pi on 4. Now, cos of 0 we know is 1 from the graph. Cos of pi on 4 we know is 1 on root 2, or root 2 on 2. So here, our values lie between root 2 on 2 is less than x, which is less than or equal to 1. So that's our domain for this function. We can use values from root 2 on 2 up until 1, and then we'll be able to evaluate tan of those values. Now, to find our range, let's substitute in our endpoints. So I'm going to find tan of 2 cos inverse of pi on 4. Cos inverse of pi on 4, we know, cos inverse of root 2 on 2, this value here, so our lower value. Cos inverse of root 2 on 2 is pi on 4. Got a bit ahead of myself then. So 2 times cos inverse of root 2 on 2, which is pi on 4. And that is equal to tan of pi on 2. Now, tan of pi on 2, we know, is undefined or infinity. So that's our highest value that we go up to. Now let's substitute in 1. So tan inverse of 2 cos inverse of 1. We know that cos inverse of 1 is 0. So I get tan inverse of 2 times 0. 2 times 0 is 0. Tan inverse of 0 is 0. So in this case, our range for this function is y is an element of, we can include 0, so round bracket 0 and up until infinity, square bracket 0 because we can include it, and a round bracket with infinity because we can't include infinity. So that is our implied domain for this function, and that is our range for this function. A basic cos inverse graph has a domain from -1 to 1. Here, this cos inverse graph has been translated to the left by 1 unit. So translated left 1 unit. That has the effect of our domain, instead of being from -1 to 1, if we translate it left 1, it's going to be -2 to 0. Our range remains unchanged because we have no coefficient out the front and we have no translation up or down. So our range is going to be from 0 up until pi inclusive. So if we go to sketch this graph, we know that our lower value is -2, our higher value is 0, which is there, and 3.14, which is there. Our halfway mark is pi on 2, 1.57, and we know that our cos inverse graph looks something like that. So this value here is 0, 0. This value here is -2 and pi. So that's our domain and our range for the cos inverse graph, and that's the shape that it will have. Now for our sine inverse graph. Let's have a look at what's occurred to this graph in terms of translations and dilations. It has been dilated factor 2 from the x-axis. It's been dilated factor 1/2 from the y-axis, and it's been translated down pi on 4 units. A sine inverse graph has a domain of, what have we got? So our basic sine graph would go from here up to here. So our domain is from -pi on 2 to pi on 2, and our range is from -1 to 1. So our sine inverse graph has a range of -1 to 1. What are the things that are going to affect our domain? This value here doesn't affect our domain, that's a translation up or down. This is a dilation from the x-axis. This value here is the only thing that affects our domain. So we can say -1 is less than or equal to 2x, which is less than or equal to 1. When I divide my 2 out, I get -1/2 is less than x, which is less than, or equal to 1/2. So that's our domain for this function. Now, forget about what's on the axis at the moment. I'm going to change that. I'm going to say that's -1/2, and that is 1/2. Okay, our range of our sine graph is usually from -pi on 2 to pi on 2. However, all of our values have been multiplied by 2, so our range would be from 2 times -pi on 2 is less than or equal to y, which is less than or equal to 2 times pi on 2, which is -pi is less than or equal to y, which is less than or equal to pi. However, it's also been translated down by pi on 4 units. So if we take pi on 4 off both of these, our range is going to be -5 pi on 4 is less than or equal to y, which is less than or equal to 3 pi on 4. Okay, so we've got our domain for our graph. We have got our range for our graph. Now let's have a look at where we can put it on. So we're going to -5 pi on 4 and 3 pi on 4. We've got to think about them as a decimal. 5 pi on 4 is just over 3.14. Maybe it's about 3.8. So -3.8, let's say it's down here. That's 1.5 pi on 4. 3 pi on 4. We know that pi on 2 is 1.57, so it's got to be between 1.57 and 3.14. Let's say it's about 2.25, somewhere around here. That's our maximum value. At the halfway mark is where it crosses the y-axis. It is a sine inverse graph. The halfway mark will be negative pi on 4. There we've got 3 pi on 4, and that's 5 pi on 4. Okay, a sine graph, it'll go from here, it'll go through here, and then our maximum value will be up here. The last thing we care about is the shape of the graph, and sine inverse curls up and then up like that. So it's going to have a curved shape like that. It's very hard to draw on one of these screens. Okay, for our graph of 3 cos inverse 2x minus 2, let's have a look first at our domain, our cos inverse graph. The values we use for cos inverse are from -1, I'll change it to black, -1, -1 is less than or equal to 2x, which is less than or equal to 1. So in this case, we're going to get -1/2 is less than or equal to x, which is less than or equal to 1/2 for our domain. So we've got our domain, our range. A cos inverse graph, my normal range for a cos inverse graph, like for a basic graph, we know y would be an element of 0 to pi. However, what's occurred to this graph, it's been dilated factor 3 from the x-axis, so our range would now be y is an element of 0 to 3 pi, because everything's 3 times as far away from the axis. 3 times 0 is 0, 3 times pi is 3 pi, and then it's also been translated down 3. So our range, down 3, it's been translated down down 2. So our range for this function, y is an element of -2 to 3 pi minus 2. So that's our final range. Okay, so once again my scale on this graph isn't very good. I'm going to say there's -1/2, and I'm going to say there's 1/2. Forget about the other ones. I just wanted to put a piece of graph paper on here and I didn't look at it too closely. Okay, it has been, we'll use the same scale here. 3 pi, we can approximate 3 pi. 3 times 3 is about 9. 3.14, that's going to be close to 9.5. So 9.5, but we know that it's been translated down 2, so let's say it's 7.5. My centre is going to be at -2 because it's been moved down 2, and my lowest value, that's not my centre, sorry, that's my lowest value, which is -2. So there's -2. The halfway mark, let's just mark it out somewhere. If we add these two things together, -pi on 2, -2 plus 3 pi minus 2, that's 3 pi minus 4. We've got to divide it by 2 to find the halfway mark. 3 pi is about 9.5. Take away 4 is about 5.5. 5.5 divided by 2 is 2.75. So let's say there's our middle point. Okay, it's a cos inverse graph. So what shape does a cos inverse graph? Well, it'll start down here, it'll go through here, and my maximum will be there. We know the general shape of a cos inverse graph is like that. Our middle point we know is 0, 3 pi minus 4 on 2. We know that our endpoint is a half minus 2 here, and we know that this endpoint is negative a half 3 pi minus 2. And that's the graph of 3 cos inverse of 2x minus 2. My implied domain is negative a half is less than or equal to x, which is less than or equal to half, and my range is from negative 2 to 3 pi on 2. Okay, here we're looking at changing the graph of tan inverse of x to become the graph of negative 4 tan inverse 3x plus 2. Okay, so let's have a look at our dilations first, let's have a look at our dilations first. So we say it's been dilated factor 4 from the x-axis, which is 4 times f of x. We say that it's been dilated factor 1 on 3 from the y-axis, so 1/3, which is f of 3x. It has been reflected in the y-axis, which is negative f of x, and then it has been translated up 2 units. Okay, so we know our basic graph for tan inverse. Our domain is x as an element of all reals. This isn't going to, the dilation isn't going to change that. The dilation from the y-axis, because it's from negative infinity to positive infinity, so that the dilation won't change the x values that we use. The range, though, a tan inverse graph, the range is usually negative pi on 2 is less than y, which is less than, not equal to, pi on 2. This has been dilated factor 4 from the x-axis, so that's going to affect these values. So I'm going to get negative 4 pi on 2 is less than y, which is less than 4 pi on 2, which we know is negative 2 pi is less than y, which is less than 2 pi. So that's, we've taken that into account, which changes our range. So from negative 2 pi to 2 pi, and it's also translated up 2. So it's negative 2 pi plus 2 is less than y, which is less than 2 pi plus 2. So that is my range for this graph. Okay, negative 2 pi is negative 6.28. If I add 2 to that, I'm going to get negative 4.28. So let's say this is our bottom asymptote. It's very hard to draw asymptotes on this. So y equals negative 2 pi plus 2. My center, we know, because the graph's been translated up 2, we know that our center is at 2, so it's got to go through 2. 2 pi plus 2 is 6.28 plus 2, which is 8.28. So that's our asymptote up here. Okay, so y equals 2 pi plus 2. Okay, we've got to remember it's reflected. So instead of having this shape, it's going to have that shape. We know it's going to approach this value up here, and it's going to go down to here. We know that our center is at negative 2. What else do we know? We know that it's been dilated a factor 1/3 from the y-axis. Because it's a tan graph, at the halfway mark between the asymptote and the intersection, somewhere around here, it would usually go through the point 1. But because it's been dilated factor 1/3 from the y-axis, it's going to go through 1/3, and then here, halfway between those, it's going to go through 1/3. So it's going to be a very flat looking graph. Now that should have been over there, like that. It shouldn't. It should be on that side of the graph, but it has to go through 1/3 and 1/3 there. I wouldn't assume that they would want you to plot those 2 points, so I wouldn't stress about it too much. I've never actually seen them ask you to sketch something like this in an exam.